Good afternoon, everyone. Welcome to the 18th session, sorry, the 15th session of the data science program. We're making a lot of progress. This is the eighth week, making it the second month. So that is, we've basically been here for 2 months, right? So we've actually come a long way and made a lot of progress. Yeah, so today we are going to be looking at continuing from where we stopped in the last class, which was on linear regression. But today's topic is going to be logistic regression. So I hope to finish these two machine learning algorithms today. So tomorrow we start with introducing the library. That is the Scikit-Learn library I told us about when while we're like introducing machine learning to us. So from there we'll start all of the coding exercise and the demonstration that we've been doing so far. So we have a lot ahead of us, a lot of interesting things to do. So just brace up. I hope you've all been able to at least revise what we did last week in machine learning, right? And linear regression as well. So we'll just be doing a little refresher before we go into the class today. All right. But before we do that, I just wanted to let us know what happened last week. Unfortunately, we were unable to get the full recording for the last class. I honestly don't know what happened. Right. I recorded the class as usual from start to finish, only to see that the recording was cut short. I don't know how, right? Because the recording was still ongoing towards the end of the class when I checked. But when Telegram sent the recording, it was about 30 something minutes recording that I was given, which didn't make sense at all. So until now, I still don't know why I didn't get the full recording. And I'm hoping that it doesn't repeat itself today because I know how important that recording is to most of us here, right? And someone was asking for the recording so as to do the assignment. The recording actually, the assignment was based on Saturday's class, not Sunday's class. So same the Sunday's class recording was sufficient or is sufficient for you to do your assignments, right? So let's just proceed, and I'm hoping that we Telegram doesn't mess up again today. Yeah, so that's just it about that. Quickly, we are going to just do a refresher on what we did last week, and then we proceed to where we stopped. So I'm going to quickly look at the assignments. Just give me a minute. I'm going to quickly look at the assignments. Okay. Give me a minute, please. Yeah, I wasn't saying anything. I was trying to set up something so we can quickly look at the assignment. All right. So now, as you can see on the screen, this was the last week assignment. So I'm just going to quickly go over it. Like these are things that are very obvious. Very simple assignment if you have been in class. Okay, so the first question here is what is machine learning? Um, So based on this, we'll know that machine learning is the first option here is the science of programming computers. No, that is not what machine learning is. Second one is the field of study that gives computers the ability to learn without being explicitly programmed. So this fits the definition I gave of machine learning. So we oh, my screen is not visible. Oh, okay. I mean, uh, let me share. All right, can you see my screen now? Honestly, don't know what's up with Telegram. All right, all right, perfect. So, the question we're just going to briefly go over them. First one is what's machine learning, and as you can see, this fits the definition I gave. The field of study that gives computers the ability to learn without being explicitly programmed. All right. So it is not the science of programming computers. It is not a type of computer hardware. It is not the practice of buying a computer. So these are just giveaway questions, like just assess your knowledge on what we did in the last class. So second question here, which of these are types of machine learning? Um, so can someone give us the types of machine learning according to what we did in the last class? What are the types of machine learning? Okay, yeah. So we have three types. We have supervised, we have unsupervised, and we have reinforcement learning. So that is the answer. We just have to select them, three of them. So that is it for that question. What's the label data? Data with specific markers, data items tagged with labels, data that is corrupted, data with categories, data. So the answer is already here, data items tagged with labels. All right. The next one, which of these types of machine learning requires labels? So, according to this question here, what is going to be the answer? Which of the machine learning type requires label? Here, exactly. So, supervised learning. Which of these are types of machine learning tasks? So, no need. Just know there is classification and regression task. Which of these is not a machine learning algorithm? We've looked at vectorization, which is it does not have anything to do with being a machine learning algorithm. Linear regression, yes, it's a machine learning algorithm. Decision trees, yes. Logistic regression, yes. So the odd one out here is vectorization. So the next question is Scikit-Learn is built on NumPy, true or false? So in the class, I told us that Scikit-Learn is built on NumPy. All right, so that's going to be true. What is the main goal of clustering in machine learning? So I need someone to answer this. What is the main goal of clustering? And under what type of machine learning do we have this clustering algorithm? Under what type of machine learning do we have the clustering algorithm? All right. So yeah. So it is under unsupervised learning. So the main goal of clustering here is to what separate data points into naturally occurring groups. Okay. So according to what we did in last class, this is the right answer. The next question here: which of these are metrics used in classification tasks? So what are the answers here? Which of these metrics here are for classification tasks? Which of these metrics here are for classification tasks? All right, yeah. So we have accuracy, we have precision on recall, and we have F1 score. So these are the metrics that you use for evaluating classification models. All right. So the other ones, yeah, mean squared error and how to, they are for regression um problems or regression models. So the last question here, which learning library is used for general machine learning? So Scikit-Learn is the answer here because these two here, they are mostly suited for deep learning problem, right? So that's when you want to go advanced. So Scikit-Learn here is more on the general side of things where you can use traditional machine learning models, right? So these questions are just straightforward. So I'm expecting everybody to get 10 over 10 here. And once you're done with the question, once you're done with the questions, you get your scores immediately, your score immediately. So you already know what you scored, right? I believe. Um, did you? Let me just confirm. Did you see your score immediately after you answer these questions? All right, all right. So you should already know what you scored. So the it will also be documented on the Google Classroom. So you should get that. Just get that today or tomorrow, anytime. Okay. So I don't know why this my screen is messing up. Okay. So that is it for the assignment. Let's quickly close all this. All right. Last week we looked at linear regression. So we introduced this machine learning algorithm, which is linear regression, and we looked at what linear regression is. Right. We looked at the linear regression formula. We looked at the types of variable in linear regression. And I said that these types of variable they are applicable to other kinds of machine learning algorithms, right? Generally, it's a general concept in machine learning, so it's not just for linear regression alone. So we looked at all of that. We looked at what regression line is, right? We looked at examples of linear regression, types of linear regressions, simple linear and multiple linear. We looked at evaluation metrics in linear regression. All right, we looked at mean squared error. We looked at root mean squared error. We looked at mean absolute error. We looked at R squared and adjusted error square. And I told us when exactly my screen is not visible. What's happening to Telegram today? I hope it's visible now. All right. So as I was saying, I was going through what we did in the last class, right? I told us also how to select the particular evaluation matrix, evaluation metric, right? And we stopped here, assumptions of linear regression. So we stopped here last week, but I explained the first one, which is linear relationship. So we are basically going to go over them just quickly, just quickly. So we're going to look at the assumptions. So assumptions are actually things that needs to be met, that like criteria that needs to be met for you to use the linear regression algorithm, right, to build your model. So the first assumption here is linear relationship, right? As I was saying in the last class, that linear relationship is a very important assumption in using a linear regression model or algorithm. What do we mean by that? The core assumption is that there is a linear relationship between the independent variable x and the dependent variable y, all right? Which basically means that the relationship should be in a straight line. There should be an increase or a decrease. If there's a kind of curvilinear relationship or something like this here, the assumption is not met, and you are not advised to use linear regression because it would not the result or the insight cannot be trusted. All right. So this is one assumption that you need to know. Although in reality we have multiple independent variables, so it might not necessarily, it might not be possible to visualize it, but you can perform a relationship like each independent variable against the dependent variable. The relation is linear. Most of the time, assumptions were actually not checked, right? Because it is just assumed. You just have to assume that okay, this is my data. The because most relationships are actually linear, unless you are working with let's say biological data or other kinds of data that you know, right, based on your domain knowledge, you know that the relationship are actually not linear. The relationship are actually probably curvilinear, or there are all different. There are different kinds of other relationships. So you already know beforehand the kind of relationship that exists between in your data. But if you don't, you can also perform or do some tests like this visualization that you can see here, plotting using a scatter plot to check how each variable relates with the dependent variable. So, but you just have to assume that with your data before using linear regression algorithm. So that is the first one, and that is the most important one. That is why we have the name linear in the linear regression, because the relationship is a linear one. So the other one we have here is independence of errors. Independence of errors. So this is actually another assumption. Um, the errors or residuals. Remember what I told us about the errors? What an error mean in linear regression? An error is the distance between the what. Can someone remind us? An error is the difference between what and what. I need responses. Who can remind us what we said about errors in the last class? Okay, patience. Patience said difference between predicted value and actual value. Adibayo, difference between trained data and predicted data. Olabode, the feature and the target. Yeah. Okay, patience got it. It's actually the difference between the predicted value and the actual value. Right? I demonstrated this in the last class, and I showed us um, how to calculate the general error, which is the total error of our model. So for a particular data point, I'm going to illustrate show us something here. After we are done with this assumption, just an illustration. I sent us a link. I don't know how many of us went through the link. So the errors here or residuals, you can also call your errors residuals, all right? So which is the difference between the actual and the predicted y values. So they are assumed to be independent of each other, all right? So once you plot the errors, you should not see a pattern like as you can see here. A pattern indicates independence. That this particular error here depends on this one. This one depends on this one. So this is this particular chart shows us that the errors are actually dependent on each other. So, but to kind of trust the be confident with what we with our model, the error or the linear regression model, we have to be sure that the errors are actually independent of each other. So once you've created your model, you can now get the error and then plot it and see the patterns that is being demonstrated by the scatter plot. So if you see something like this, a random distribution, then you can be sure that the errors are actually independent of each other. So these are just things that assumptions that needs to be met. The other one here is almost scarcity, right? This is a mouthful. This is something that um um I don't know, but anyways, what this means is that the variance of the errors should be constant. The variance of the errors. So I like how the visuals here are explaining it better. So once you plot your error, right? Once you plot your errors and you check the distance at a particular point and come to another point and check the distance. The distance between this point and this point should not be so different, right? That is basically what we mean by very low variance. Like there's no much variation in the errors that we have here. Unlike this one, the distance between the error here and the error here is not the same thing as the error here and the error here. So the errors here and the errors here. So we can see that there's actually a spread. That is what it means. Like there's a spread of the residuals, right? But what we need is a constant a constant spread, right, across the residual or the regression line here. So this is what we're expecting to have. So all these things are just, you might not necessarily be looking out for them. You might not test all of them. So that's what they're called assumptions. So once before you choose your when you choose your regression model, you are assuming all these things that we're going to be looking at to have been met or to be true. All right. So the time you will now start to, like, let's say, go deep to check the assumptions is when you are seeing your model performing poorly. Like a model is not giving you what you want, then you now start investigating to know why your linear regression model is not giving you the results you want, all right? So in that case, you might now start looking at all the assumptions to be sure that the model or the data and the output of the model, like the errors that we have here, all of them meet these different assumptions. So the other one we have here is normality of errors. So we have looked at three assumptions now that are all based on the error. So I told us what um a normal distribution is, right? So once you plot your errors using histogram, you should get a normal distribution or an approximately normal distribution. So that is another assumption. If you don't get it, if you get something like this is not a normal distribution, you cannot rely on the result of your model. All right, you have to ensure that your errors are normally distributed or approximately normally distributed. So you can see here that a normal distribution allows for reliable statistical tests used in linear regression. So linear regression is a statistical technique that have been adapted into machine learning. So there are a lot of things that needs to be met statistically so as to rely on the results, all right, of the model or the final model. We have another one which is called no multicollinearity. All right, no multicollinearity. Multicollinearity basically mean that it means that we have a situation where the independent variables are correlated with each other, highly correlated with each other. All right. So in that case, we might not we might have a problem, all right, with the results. So we need to make sure that there is no multiple collinearity, and there are ways to check multiple collinearity. All right. We can use VIF. VIF is variance inflection factor. So all these things are actually advanced investigation that you can perform. So, but you just need to know all these assumptions, all right? Most of the time, you would not be looking to check all these assumptions. Trust me. Like, I won't even be asking you in the course of the assignment to check the assumption. It's just something you need to know in case there's a need for you to investigate your model, right, and be sure that they meet the assumptions. But generally, you come with that that's why it's called assumption, right? You come with that mind that okay, your data actually meets all the assumptions. So let me just linear regression, and then you get your results. If the metric or the what you're getting is not good, the performance is not good, then you can start making sure that that the um, assumptions were met. If they were not met, then you can go and use another algorithm to create a particular model. So that's for multiple collinearity. So this refers to the situation where the independent variables x are not highly correlated with each other. All right. So that is for no multicollinearity. Multicollinearity is when the independent variables are highly correlated with each other. So the reason why we have are not highly correlated because it is no multicollinearity. So if X variables are strongly correlated, it can lead to difficulties in isolating the individual effect of each variable on Y. So we want to understand how each variable is impacting or affecting the label, that is the dependent variable. So when you have highly correlated features, it will be difficult to separate them to know which one is having a particular effect on the y variable. All right, so that's why we need all of them to be independent. Basically, that is what we need. We need all the features to be independent of each other. They should not be correlated. All right, if there's correlation, you just have to drop one of those variables. Right, if let's say height is highly correlated with weight, you can just drop one of them because they are basically doing the same thing. For the fact that they're correlated, that means they are having the same impact. So dropping one is really not going to change anything. So that is for multicollinearity. So we have another one, autocorrelation. So no autocorrelation rather. In this case, we are also talking about the errors. So errors are also known as residuals, as I've said. So in this case, the errors or residuals are assumed to be uncorrelated with each other. So this is almost similar to what we have here, independence of error, right? So these are actually almost the same thing, but we see that this one means that the error for one data point doesn't depend on the errors of previous or subsequent data points. I think they are actually the same thing. They are still saying the same thing, independence of error. Because if the errors are independent, they will not be correlated with each other. So you can just consider this number six to be the same thing with this independence of error. So those are the assumptions for linear regression, right? So these are the things that these are the criteria that have to be met for your model to be to perform well, right? If you don't meet all these assumptions, your linear model might not necessarily do very well, right? It might not do very well. So in the case where your linear model is not giving you the performance you need, you can now start to investigate to check if all these assumptions are met. If they are not met, then you can now resolve or resort to using a different algorithm. We're going to look at other algorithms in subsequent classes. So let's look at this final note here. It's important to remember that these are assumptions, all right? And real world data may not perfectly adhere to them. So, but however, checking for these assumptions and addressing any violations can help improve the reliability and interpretability of your linear regression model. All right, so there are techniques to available to handle some violations like data transformation or using alternative algorithms for non-linear relationships. So you can see here that if some of these things are not met, you can resort to using alternate algorithms in case where you have non-linear relationships, or you can perform data transformations on your data set to kind of make them to fit a particular pattern. Let's assume maybe you want to make it to be normally distributed. There are techniques you can actually apply to your data to make it normally distributed. So these are the things you just have to know. Yeah, that is it about linear regression. It's the starting point for everything we're going to be doing. So most of what we've talked about here are transferable knowledge. So if you understand everything we've talked about so far in this particular on this particular topic, the subsequent ones would not really pose as a challenge, right? Especially what we're going to be looking at today, which is logistic regression. So that's going to be it for linear regression. And before we move to logistic regression, I'm quickly going to do a little demonstration. So please, can everyone see my screen? Can you see my screen? Anyways, I don't know what happened, but the attendance or the participation has reduced a lot. It has actually reduced. I don't know if it is the difficulty or life challenges or some other things. But I when we started, we usually have up to 120 persons in the class, 130 persons. But now we're having just 75 people. And the thing is that the assignment submission, the last assignment that I gave, we have up to 120 people or persons that submitted. So I'm wondering where the remaining persons came from, because right now we're having just 75 people, and then for the assignment we're having more than 100 assignment submission. So I really don't know how that is possible, but um, if if probably there are some persons that don't attend class but watch the recording later and do the assignments, you just know that you are losing a lot of mark from the attendance, because the attendance carries a lot of mark. It carries a portion of your total mark. Anyways, That's just by the way. So as you can see on the screen here, we have um wait, so network is bad. Is it currently? Did it just start or has it been so since I've been okay? Um, please let me please. I need to be sure if you can hear me clearly and see my screen clearly. Okay, okay. Thank you. All right. So as you can see here, this is an example of it's an example of a regression line, right? I'm going to just explain some of the things that we've done so far. We've explained so far in linear regression. So in this case, we have so in this case here, let me get all right. So in this case here, we have our x and y axis. All right. The reason why we're having this spillover into this place is because we have negative values. All right. So, but this is basically what a regression line would look like. So, what linear regression does is that it tries to fit this red line you're seeing here, it tries to fit it. If I click on this show regression line, it's going to show me the best line that fits this data. So, this blue line you're seeing here is the best line. And how do you determine the best line again? You determine the best line by calculating the sums of square error or the error. Let's just use error so as not to confuse you. You calculate the total error of all the data points and what you depending on the particular metric you're using. You either square it or do the square root of the square, or you get the mean absolute error and all of that. But normally, what we do is just to square each of our error and get the mean or the average. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 observations in this particular model, all right? Just like having 15 rows. So we plotted the x, that is the independent variable, against the y. We plotted the y against the x, right? And we got this relationship. So after you plotted it, then you now what linear regression tries to do is try to get a line that fits the the data. So if you remove this regression line, what linear regression does that it starts randomly, right? It starts randomly. It draws maybe this red line. It just draws a red line here. Calculates the sums of squares. So this SSE here means sums of square error. And this value that we're having here, 7.84, is the error. All right. This is the lowest error that you can get for this particular data. And this particular one that is red is the current line that is here. So this line is the aim of this thing is to bring this line close to this particular error from 30 to 7. So if we can move it from this point and this point here. I'm just showing you how you can. I'm just demonstrating how you can do it yourself because I would like everybody to do this. So you just gain intuition on what linear regression is. So if I move this up here, you can see that the error is changing. You can see that the error is changing. It's changing, it's changing, it's changing, it's changing, it's changing, it's changing. You can see that the point to start increasing back. Can you see? So you have to bring it back again. You have to bring it back again to that particular point. So I think it should be around here, 7.8. This is the line. You can also move this down part. Let's see if it's going to change anything. So moving it. Okay, so just have to leave it here. All right. Now, this point at which the regression line touches this particular y-axis, this line is the intercept. All right. So if we move this line, you can see I'm shifting it. The intercept is changing, but the slope is the same. All right. The slope is the same. We're not bending it, but we're just moving it and changing the intercept here. If we just bend it at the point, the slope and the intercept would be changing at the same time. You can see. So all those things are what is being calculated. The calculation will be done based on the formula I showed you, which is y equals to what? Beta 0 plus beta 1 times x1 if you have just one variable. So those beta 0 has a value, all right, and beta 1 has a value as well. All right. So all those values would be calculated when you want to make your prediction. So these are the things that are being done when linear regression model is being trained. So it is not going to be visible like this. So this is what people did to just make us understand exactly what is going on under the hood. So this is a good visualization to help you understand it. You can change the data, you can randomize the data, all right? So you can get different data points. So you can just play around with it to see how we show the regression line. You can see where the regression line is. This is the particular point. So you have to drag it and bring this one down to this point. So you see that this is the perfect line here that minimized the error. So you need the line that minimize your sums of square error. So that is what linear regression is trying to do. So the linear regression name is also called least squared error, right? Least squared error, because you're looking for the error that is the least basically, because you try different lines and you calculate their error. So the error that is the least among all the errors that you've calculated is the model or the line that will be selected. So that is it for linear regression. You can see I send the link to the Google Classroom. I don't know how many of us saw it, but it is there. You can just play around with it and understand. I think it will help you understand better what linear regression does. So for today, we are going to be looking at another machine learning algorithm, which is logistic regression. Okay, so we are going to be looking at logistic regression. Now, I believe this will be for you to understand because we've already done linear regression. So logistic regression is like a brother to linear regression, right? We're going to look at what logistic regression is. We're going to look at logistic regression formula. We're going to look at sigmoid function. We're going to look at types of, this should be logistic regression. There's a mistake. Logistic regression. Types of logistic regression and evaluation metrics in logistic regression. Okay, evaluation metrics in logistic regression and also assumptions of logistic regression. So yeah, it's going to be an easy one to understand because of the foundation we've laid already in linear regression. So there are a lot of diagrams in this particular class and this particular topic that would help us understand what is happening. So first off, I introduced the topic with a diagram differentiating linear regression from logistic regression. So can someone just remind us what particular task logistic regression is used for? I don't know if it's just me, but time is actually fast today. No, it's okay. Okay. Um, Classification task, binary problems, numerical task, categorical classification, categorical logistic regression is used for binary classification problem, category, predictive analysis, and categorical variability. All right, so I think we all have an idea of on what logistic regression does and which task that it is used for. So those that said classification tasks, you are correct. Um, People that said binary problems, you are correct as well. But logistic regression is not only used for binary problem. Classification task is not just for binary not just for binary problem. You can have more than two output or two categories. All right. So in that case, you can also use logistic regression. So we are going to see that as we move forward in this particular class. So yeah, let's just proceed. So now you see these two diagrams, right? You see we have one here which is for linear regression, and the other one here was for logistic regression. You can see the difference between the line. So the line here is actually the model. All right. The line here is also the model. In linear regression, the line is a straight line. All right. In logistic regression, the line is an S-shaped line. If you look at it, it looks like an XS. So it's called S curve or sigmoid curve, right? So this is what logistic regression does. You can see that this fits, and in this case, we see the kind of data that is being used. We have 0, that is class 1. In this case, binary problem, and we have class 2, and we plotted it on a chart, and we can see how it is being plotted. So how do we fit this kind of categorical data? It is not like the other data that has data points spread everywhere, right? This one is on one side and this one is on another side. So how do we do that? The best we can, if we try to use a straight line, which is linear regression, we will not get our desired result. It's not going to work, all right? So an adaptation we had an adaptation of a linear regression which adapted or which kind of brought a new connection or line, so to speak, right? To okay, so just give me a minute. Okay. All right, thank you. So as I was saying, the logistic regression is an adaptation of the linear regression where it uses a sigmoid line or an S-curved, S-shaped line to map the relationship, all right, between the independent variable and the dependent variable. So you're already getting the difference. One difference is that this is a straight line, the model is a straight line, and the logistic regression, the model is an S-curved or S-shaped line. Okay, so we're going to see how that makes sense as we proceed. So this is the major difference between linear regression and logistic regression. Okay, so let's just move forward. What is logistic regression? So logistic regression is a statistical method. Um, this should be for classification problem. So logistic regression is a statistical method used for classification problems. All right. So, but initially it was used for binary classification problem, but there was an adaptation where it can now be used for more than two categories. That is why when you see the definitions, they usually refer to binary classes. All right, that is yes or no, because that is a general idea of classification problem. But there are some situations where you need or you have a categorical variable there are more than two categories. So there was an adaptation of that, and we can also use logistic regression to also perform that or solve that particular task or problem. So, but just for you to understand, in case you're seeing binary everywhere here, so it's a statistical method used for classification problem. Unlike linear regression, which predicts a continuous outcome, logistic regression predicts the probability of a binary outcome. Okay, may not make sense now, but just follow me. So what logistic regression does is that it predicts the probability of a binary outcome, which means two possible outcomes such as success and failure, yes, no's, or 0 and 1. So most of what you'll be doing, most of the classification problem you'll be doing, they are usually binary problems, all right? They're usually binary problems. So that is why you are seeing all these examples here. Okay, so let's just move on. It is widely used in various uses as medical diagnosis, marketing, finance, for tasks like predicting disease presence, customer churn, or default on loan, or spam detection as well, where it classifies whether an incoming mail is a spam email or not. So those are examples of classification problem that you can use linear logistic regression on. Okay. So logistic regression is used for binary classification where we use sigmoid function, right? So this sigmoid function is going to be the focus or the focal point of logistic regression. The sigmoid function is what differentiates logistic regression from linear regression. All right, so just keep that at the back of your mind. So the sigmoid function takes as input the independent variables and produces a probability between 1 and 0. So what happens is that, let me just give you an idea of how logistic regression is an adaptation of linear regression. When you use your linear regression to make prediction, what do you get? You get a continuous value, right? You get a continuous value that basically does not have a range, right? But to make that logistic regression, you take that continuous variable and you pass it into what we call the sigmoid function. So what the sigmoid function does is that it kind of restricts the output to be between 0 and 1. So no matter the input that you give the sigmoid function, if you like give it 9, or you give it 90,000, or you give it 900,000, any value you give it, it's going to compress it. That is a function basically, right? So it has a formula. It's going to compress it to be between 0 and 1. So let's assume you give it a value and it gives a probability value of 0.36. So 0.36 is like 36%, right, probability. So 0.36 now, based on your classification, would now be classified as either 0 or 1. And that classification is dependent on what we call threshold. So threshold is like, which point are we going to consider it to be in the class 1 or class 0? If your threshold is 0.5, that means from 0 to 0.49 would be what? Class 0. And then from 0.5 to 0.21 will be class 1. So in this case, if our probability output is 0.36, that means the class that is being predicted is what? Class 0. All right. If the output probability value is 0.98, all right, the class that would be the the class that will be predicted is going to be the class 1. So you have to understand the importance of, let me just create a new notebook so I'll explain writing it out. All right, so as I was saying, we have what we call threshold. Okay, so the threshold is what determines which class probability value will fall in. All right. All right, sorry for that. So the threshold determines which class our probability value will fall in. So let's assume our threshold value for a particular model, we set our threshold value to be equal to what? 0.5, which is the same thing as what? 50%. So, and our sigmoid function, we take in, let's say, a value like an input, all right, and it will now give an output of, let's say, 0.76. And in this our threshold, what this 0.5 threshold means that anything between 0 and what? 0.49 is in the what? Is in class 1. Let's say in this case, class 1 is what? Yes or no. And anything between 0.50 and what? 1 will be in what? Class 2, which maybe in the case of your task might be yes. So, and we now have our sigmoid function now, right, giving us this particular probability value. So which class will this prediction be placed in, right, based on this threshold function that we've defined here? Which class is this prediction going to be placed in? This 0.76 prediction, is it going to be placed in class 1 or class 2? Exactly, right? So we're going to have this to be in what? Class 2. But now, if we change this threshold function to be what? 0.8, and this one becomes, if we change the threshold function to be 0.8, which class are we going to have this? So you can now see how the threshold determines which class our probability value will fall in. All right. So that is something to note in logistic regression. You need to know what threshold is. You need to know what sigmoid function is. You need to know what probability values are, and you need to know how the outputs are placed in their different classes based on the threshold that based on the threshold value, basically. So, but by default, the threshold is usually 0.5, unless you want to change it. So let's just proceed. So we have so as I was saying, the logistic regression is used for binary classification, where we use sigmoid function that takes input as dependent variable and produces a probability value between 0 and 1. So for example, For example, we have two classes, like class 0 and class 1. If the value of logistic function for input is greater than 0.5, then it belongs to what? Class 1. All right. Otherwise, it belongs to what? Class 0. So it is as regression because it's an extension of linear regression, but is mainly for used for classification problems. So this is the core concept in logistic regression. If you understand this, then you've understood logistic regression. So you need to know that logistic regression is an adaptation or an extension of what? Linear regression. So let me just put this. So now we're going to look at the sigmoid function. Right. What does the sigmoid function do? So the sigmoid function is a mathematical function used to map the predicted values to probabilities. That's it. All right. I've explained this before, but I just want us to go over it again because of its importance. The sigmoid function is a mathematical function used to map the predicted values into what? Probabilities. And I told us that probabilities are between, or we all know that probabilities are between 0 and 1, right? If something has a probability of 1, that means the chance of it happening is certain, that it must happen. That is what 1 means, all right? If you say the probability of rain falling tomorrow is what? 1. That means rain will fall tomorrow. It has to fall tomorrow. Like that is just what it means. If you say the probability is 0, that means it will not fall tomorrow. If you say the probability is 0.7, that means there's a high chance, right? There's a high chance that rain will fall tomorrow, but you are not certain. All right, you are not. So that is basically what probability mean, and the value or the range is between 0 and 1. And sigmoid function is a mathematical function that maps any value into probabilities. That is 0 and 1. So it is not just used for logistic regression, it's used in other areas, right? But it's something that was picked and applied to give us logistic regression. It was a mathematical concept that was that was picked and then adapted to give what we have here as logistic regression. So it maps any real value into another value within a range of 0 and 1. So the value of logistic regression must be between 0 and 1, which cannot go beyond this limit. So it forms a curve like the S form curve. So that is what we have here. So if you look at this, you can see that these are actually predictions. All right, all these things that you have here, they are predictions. So they don't go beyond 0 and they don't go beyond 1. So once it gets here, it's just going like this forever. Like it is not going above it. All right. So this is the sigmoid function. So this sigmoid curve is as a result of the sigmoid function that we have. All right. So let's say we have a value here. You have a y an x value here. You can just map it and just trace it to here. So this 0 to 1, these are probabilities. This all the from 1 to 0, they are probability values. So if you have if you trace x here and trace it to this place, let's say it's 0.2, all right, and your threshold is here, that's 0.5, then it will belong to class 0. If we have the value of x to be here and you trace it up here, you can. So this is just the same concept as linear regression. It's just that it has a sigmoid function that takes the input of numbers and convert them to be between, or map them to be between 0 and 1, so that they can be used for classification. All right. So that is for sigmoid function. So this is the formula for segment function. So you don't need to know this. This is what segment function looks like mathematically, right? So it's not necessary that you know it because you won't be writing formulas, right? So we're now going to look at the types of logistic regression. Types of logistic regression. So we have three types of logistic regression. Same way we have two types of linear regression. So can someone just remind us the types of linear regression? Types of linear regression. Okay. All right. So that is actually it. So we have simple and multiple linear regression. I don't know why people are saying single. It's simple. Let's check it here. We have simple linear regression and multiple linear regression, not single and linear regression. So just take note of that. So in logistic regression, we have three types. All right, we have binomial or binary, right? We have binomial logistic regression. So in when we look at the actual we can actually also call it binary. All right, so let me just binary. So either of the two is acceptable. Binomial, binary, they are saying the same thing. So in binomial logistic regression, there can only be two possible types of dependent variable. So in remember in linear regression, um classification the classification of the types of linear regression was based on the number of X, that is the independent variables. But when it comes to logistic regression, the classification or the criteria for categorizing them into different types is based on the numbers of categories. All right. So just taking that's another difference. So for binomial or binary, we have or we can use this particular logistic regression when there can only be two or when there are only two possible types of dependent variables or categories in your dependent variable, such as 0 or 1, pass or fail. All those examples that have been given before, right? So this is the situation when we use binary logistic regression. So this is the default logistic regression that we are going to be doing. This is default, right? This is just default. So we have another one called multinomial logistic regression. All right, multinomial. So this multinomial logistic regression is used in cases where we have more than two categories, and specifically more than two unordered categories. Unordered meaning there is no order to the categories. That means the category doesn't have any inherent rank. You understand? I'm going to explain that. So, for instance, you might have categories like um, you want to be able to predict the type of transportation a person will choose. So, the categories you have are car, bus, train, or bike, right? Or let's say car, bus, train, or bike. And we have four categories in this case. We are not going to use binary logistic regression. It is not going to work because binary logistic regression requires you to have two categories in your dependent variable. So you're not going to have to resort to using multinomial logistic regression, which allows for more than two categories and specifically more than two unordered categories. In this case, bike, train, bus, and car, they don't have any rank, right? They don't have any kind of order to them. Understand? So they are just there, different categories that are independent of each other. But now, looking at the third type of logistic regression, you see that in this case, it's the same thing. We are using it to predict more than three categories, but the categories are the categories here are actually ordered, right? In this case, we have low, medium, and high, right? Maybe we want to predict the level of satisfaction, customer satisfaction, all right? We can have, okay, low, medium, and high. So you know that this category, they have a rank. Low is what is on the lower side, medium is on the higher side, high is on the highest level. So there are levels to the categories in ordinal logistic regression. So for you to select the kind of logistic regression to be used, you need to first look at your dependent variable, assess it, make sure that you know the nature of that dependent variable before selecting the particular type of logistic regression to apply. If it's just two categories, go for binary logistic regression. If it's more than two categories that are unordered, all right, they don't have any level, understand, you use multinomial. But if there is an order, if there's a level, there's a rank to the categories, understand, then you can now use ordinal logistic regression. Hope you understand. Hope everyone is still following. Hope everyone can still hear me clearly. Okay. So let me just give maybe another example of ordered categories. For instance, let's say you want to you have a category that is an educational level. You have elementary school, high school, bachelor's degree, and master's degree, and PhD. So these are like five categories of six categories, and these categories they have an order. There's a rank, all right. There's a rank, inherent rank in this category. So in this case, you use ordinal logistic regression if that is the particular problem that you want to tackle or solve. All right. So another example can be, let's say, socioeconomic status, low income, middle income, high income. This is an example of ordinal. There are levels to the different categories. It's not just like normal category like cat, dog, or sheep. There's actually no order to it. You cannot say sheep is greater than cat, or dog is lesser than sheep, or dog is lesser than cat. You cannot actually perform that kind of comparison with unordered categories. So just understand this difference and you'll be able to appropriately select the type of logistic regression for your problem. So in Scikit-Learn, we are only going to be doing binomial and multinomial. Scikit-Learn doesn't really support ordinal data, right? So, and yeah, it doesn't support ordinal data. We use a different library for that. So you only be looking at binary and multinomial. And most of the time, what you'll be performing is binary classification mostly, right? if if you don't, maybe sometimes you might have multinomial problems and you can just use that multinomial logistic regression for it. So you see that the implementation in Scikit-Learn is very straightforward, very straightforward when we reach there. So you need to understand all this foundation that I'm trying to lay now. So once we start the coding aspect, you'll not be confused, right? So the next thing here is evaluation metrics. We're going to be looking at the different evaluation metrics in logistic regression. So remember we looked at the different evaluation metrics in linear regression. So the same thing will be done in this particular type of machine learning algorithm. Someone said my voice is cracking. Please can and someone confirm. Classroom, can you confirm if it's happening on your own end too? All right. Okay. So now we're going to look at evaluation metrics. Before we go into this particular one, can I get response to the to this question? What are the different classification metrics for regression problem? Right, we looked at it in the last class. So we have about, I think, 4 or 5 of them. So what are the different classification evaluation metrics for regression problem? Just list them. I need more responses. I don't know why we are not responding very well today. Is it the weather? Okay. Um, mean square, root mean square, or mean absolute error, MSC, RMSC, MAE, R square, mean squared error, mean absolute error. Okay, I think we are good. So there, those are the errors you'd use for regression task: mean squared error, root mean squared error, mean absolute error, R and R square. All right, so these are the most common. These are the metrics you'll be using basically. All right, so that's fine. That's fine. Also, we also have adjusted R squared. Okay, so today we're going to be looking at the evaluation metrics in logistic regression. Okay, logistic regression. Now, the first one here is confusion matrix. Right, I don't know why I'm starting with this. It should be accuracy first of all. So, we are going to look at accuracy here first. So just give me a minute to do this. All right, so let's just continue. So the first one here is what we call accuracy. So let's see that. So the accuracy is the ratio of correctly predicted right, to the total instances, both true positive and true negative. So what are we saying here? So if we look at the predicted values, all right, and we look at the actual values, we can calculate the number of predicted values that are actually accurate, right? And we are going to just divide it, right? We're going to divide it, compare it to the total instance, and we'll get a value, an accuracy value. Let's say 80% of predicted values are correct. That 80% is your accuracy score, right? So you are looking or you are putting into consideration both the two classes, right? Both the positive class and the negative class. So if out of 100 predicted values, only 65 of them were predicted correctly when compared with the actual value. So that value, that 65% would be considered your accuracy. All right. So the other way to do it is just to divide the total correct prediction over the total data points. That is the total number of your label, and multiply it by 100 just to get your accuracy. So the accuracy is like the go-to is the go-to metric, the first metric basically that you will use to assess the performance of your model. If your model have an accuracy score of 90%, that means 90% of the time your model will always predict or make an accurate prediction. You understand? 90% of the time your model will always make an accurate prediction. That means, let's say if you make a prediction 10 times, out of that 10 times, 9 of them will be predicted correctly and just one will be wrongly predicted. Let me give a practical example. If you are if you have a model that is classifying spam email and non-spam email, and if your accuracy is 90%, what it means that if 10 emails enter your inbox, out of those 10, let's say out of those 10, 9 of them will be correctly classified to whether it is spam or not spam. And one out of that 10 will be wrongly classified. So in that case, you might see some email that are not spam, all right, but they are in your spam folder. For example, some of us that got this youth drive program, I'm pretty sure that you have to check your spam folder for the email, and this email that was sent is actually not a spam. So that is a problem on the model part. The model is not 100% accurate. It makes mistakes sometimes, right? So depending on the level of accuracy, to determine how much mistake your model will be making when making classification. So that's an example. Another example might be in the case of diagnosing medical diagnosis. All right, if you give your model, you train your model on detecting tumor or something. All right, maybe brain tumor. If your model accuracy is 80%, that means that 80% of the time that you show your model an image or a CT scan of the brain, 8 out of 10 times it will correctly classify or tell you whether there's a tumor or not. And the remaining 2 times is going to mislead you. So if there was a tumor, it's going to tell you that there's no tumor. But if there was no tumor, it's going to tell you that there's a tumor. So this is what the accuracy means. So you should always aim at getting the best possible accuracy. All right, that is the aim. You are aiming at getting the best possible accuracy score. But now there's a catch. There is something that you need to note. Accuracy is not everything. All right, accuracy is not everything. Accuracy is a useful metric, but can be misleading if the classes are what? Imbalanced. Now, this is a very, very important note to take. There's what we call imbalanced data sets, as you can see here, right? Let me go back here. So we have imbalanced data sets does not go with accuracy. So when your data set is imbalanced, don't even try to use accuracy as a metric because it will be a very misleading metric. You understand? So for instance, let's say you have a data set that you want to train. You want to use data set for training, and it has two categories: class 1 and what? Class what? 2. Okay. So in class 1 has let's say 450 instances, and class 2 has only 50 instances. The total number of data points, total classes, or total records or observation, let's use observation, is equal to 500. All right, this is the size of your data set. And out of these 500 observations, only 50 of them are in class 2. The remaining 450 is in class 1. This is a highly imbalanced data set. This is what imbalanced data set mean. Imbalanced data set is usually used in data set that that has classes or categories. All right. So in cases where you have imbalanced data set, accuracy is not a good metric. It is not a good metric. Do you understand? So we would make sure that our data set is balanced. So for instance, if we have let's say 300 in class 1, and we come here and we have 200, this is a fairly balanced data set. It is not, you can actually use accuracy as a metric, all right? It is still good. But let's say when you have let's say 350 and you have 150, now this is actually not balanced. So you might not, your accuracy score might not be a very good metric for assessing your model performance. So these are the things you need to pay attention to. Machine learning is more than just writing the code and training your model. You have to understand all these things. You have to know when to use a particular metric. You have to know which algorithm to use. You have to understand how your data set has to be structured, and a whole lot of other things. All right. So these things are the things that make you a good data scientist, not necessarily knowing how to use Scikit-Learn. You understand? Because we are going to look at it and you see how easy it is to use it. Right. So that's why I'm trying to lay this foundation, so you gain intuition, you understand it very well. All right. So this is the idea behind an imbalanced data set. So that's for accuracy. So your accuracy is what we've discussed here. So if your data set is imbalanced, please don't use accuracy. So we have confusion matrix. I'm trying to put this at the end because this confusion matrix. So let's quickly look at precision and recall first before going back to confusion matrix. So because the confusion matrix is based on precision and recall. All right. So we have precision. Precision is another metric that is used in classification task. I'm going to repeat it. It is another metric that is used in classification tags. If you are into research, if you are into all this, if you've been doing statistics before now, you should have an idea of what precision is, right? So precision is also known as positive predicted value. All right, positive predicted value. So precision is before I explain this, just know that this precision explanation can be tricky to understand. All right, but just follow me. So precision is the ratio of true positive predictions total predicted positives. I'll say it again. Precision is the ratio of true positive predictions to the total predicted positives. Now, let's quickly look at how that. Okay, before we go into that, it basically measures the accuracy of the positive predictions. So, what you are focused on in precision is positive predictions, right? You're looking at how many of the positive predictions are actually accurate. Do you understand? Let me quickly just illustrate it here. Precision, precision, positive predicted value. So precision is focusing mostly on the positively predicted value. Let's say in we have two class, positive class and what negative class. All right. Now let's say in this positive class we have, let's use 70. Negative, let's use 30, making 100. So these are the actual value, all right, actual values. So now after you've trained your model, you now start making predictions with your model. Recall me as a predicted values, all right. So for positive, out of 100, just 60 of them, or let's say 80 were predicted to be positive, and then negative we have 20, right? So you can see now that there's a disparity between the actual value and the predicted value. So in this case, we have 80 values that are what positively predicted, and in the positive case we have 70. So what precision does is that it looks at only the positively predicted value. It does not focus on the other class, right? Okay, let's assume you have class 1 and 0. Class 1 is the positive class, 0 is the negative class. You have yes and no. Yes is the positive class, no is negative class. So just like that, you have spam and not spam. Spam is what? The positive class, and not spam is the negative class. So the category that you are trying to get, that particular category, is your positive category, and the other one is your negative category. Let's say you want to predict whether an image or something is a cat or not. Cat is what? The label cat or the category cat is what? The positive class, while the category non-cat, not cat, is the negative. All right, so that is just the idea between positive and negative predictions. All right, so let me even just make this yes spam, or so you have a better understanding. Not spam, right? Spam and what? Not spam. In this case, which particular label or which particular category is the positive category and which one is the negative category? All right, exactly. I think we understand it now. So spam in this case is positive, and not spam is what? Negative. So let's just continue. So in this case now, we have the spam number of values that are spam in our actual data set is 70. But when it came to the predicted values, we have what? 70, 80 rather, right? We have 80, all right? So to calculate the precision, what you are going to focus on is this spam. This is the positive, let me put it in the brackets. Positive, positive class. So what is the definition of precision again? Precision is the ratio of true positive predictions to the total predicted positives. So I'm going to give you a few seconds to look at this definition again, because you are going to tell me how we are going to calculate the precision from these values we have here now. So precision is the ratio of true positive predictions to the total predicted positives. All right. So now, based on this definition now, what is going to be the precision here? What is going to be the precision here? Looking at these values here, what is going to be the precision? Anyone? I'm just going to give some few minutes so that more persons would answer, because I just want to know if we understand this particular metric. Very, very important. Very, very, very important. Okay, okay. I think I'm just going to stop here. Now, I'm actually impressed because most of us got it, right? The precision is going to be what? And precision, recall, all of them, they are between 0 and 1. All right, the same thing as accuracy. Accuracy can be between 0 and 1. So your precision here is what? 70 over 80. Like Sunday got it 7/8, which is the same thing. Aniche Enare got it too. Okoli Precious, Tijani, Bamishe. So yeah, that's actually very impressive. I think we're understanding this, so that is to show that we're actually understanding what I've been explaining. So this, how did we? For those that don't understand, how did we get this 70? This 70, I remember I told you for precision, we are focusing on the positively predicted values. So we predicted 80 out of 100 to be positive. So in this 80, how many of these values are actually positive? So we're not going to look at the actual value, and you can see that 70 is only 70 that are actually positive. So that is going to be the that's what we're going to have as the numerator, all right? And then we're now going to say, okay, now out of how many total positive, how many total of What's the total number of positives that were predicted by our model? We have here 80. So it's going to be 70, which is the correct positive labels, over 80, which is the total number of predicted positive. So this is going to give us 0.875, which is the same thing as what? 87.5%. So our precision now will be what? 87.5%, which is good. All right. It is actually very, 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 very good. Our precision in this case what is 87.5%. Now we are actually focusing on something specific. So there are instances where precision is very, very, very important. There are some tasks that you want to make sure that your model is predicting the positive classes very well, very, very well. Let's say in medical diagnosis, you want to make sure that your model is able to correctly predict the image to be maybe you are creating a model that can predict whether there's a tumor or not. You want to make sure that your model is correctly predicting that positive class. So you focus on the precision metric. You want to make sure that your precision metric is as high as possible. Now, forget accuracy, all right? Because you are focusing on the positive class. So you want to make sure that your precision is very high. In this case, our precision is 87.5%. Understand? So this is just what precision is all about. All right. So let's now look at recall. So recall is the other twin of precision. Recall. So let's quickly look at what recall is. So recall is also known as sensitivity or true positive rate, TPR. So recall is the ratio of true positive predictions to the total actual positives. The same thing I'm going to do, and I'm going to allow you to tell me what the recall will be based on the values there. So let me just look at this again. Recall is the ratio of what? True positive predictions to the total actual positives. I'm going to say it again. So what does recall do? It measures the ability of the model to identify all relevant instances. So recall is important in a situation where the cost of false negatives is high. Okay. So this is what the definition of recall. So if we come here now, and based on this, let me just put recall here. So based on this, what is going to be our recall? Based on this value here, the same process as precision, but based on that definition, what is going to be our recall? All right. Okay. So I think most of us here are saying recall is what is it from 80 over 70, 8 ratio 7, 70 over 8 over 7, 8 over 7, 70 over 8. Only one person got it though. Only one person got it. Let me go back to the definition. Now I'm going to answer it, right? Recall is what the ratio of true positive predictions. All right. So we're going to what's the true number of true positive predictions here? So this is our predicted values, right? What is the number of true positive? It's just we're not looking at the positive predictions. We are looking at the number of true positive um predictions. So it's going to be what 70. All right, over the to the total actual positives. What is the number of total actual positives? Here is what actual value. So the actual positive here is spam, which is what 17. So recall in this case will be what 100%. Can everyone hear me? Can everyone hear me? Please let me know if everyone can hear me. Yeah, so kudos to Patience. Patience was the only one that got this. That is she says 70 over 70. So you can now see the difference between precision and recall. Precision focuses on just the predicted value here and the positive class. But recall focus on the number of positively true positive predictions and the total number of positives here. So let me even change it. I'm going to change it. So in this case, um we have let's say 150. Let's say we have total number of 300 observations. Observations. We have 150 for spam. But let's say we have 200 for spam and we have 100 for not spam. All right. So in this case, we now have let's say 175 for true. And in this case, we have what is going to be I think 125 or so. 125. So what is going to be the precision and recall? I need the answer in percentage. So what's going to be the precision and recall for this new data set and these predictions that we have here? What's going to be the precision and recall? I need the answer in percentage, not in ratio. So let me just put it here. Precision is equal to this and recall is equals to this. Okay. All right. So because of time, we'll just have to stop here. Okay, great, great, great. I think I've seen a correct answer. I've seen a correct answer. Only one person has gotten it so far. Okay, let's look at it together. Let's look at it together. Now, there's something you need to know. Precision or recall or accuracy, they cannot be above 100%. That is just one thing you should know. They cannot be so everybody getting 114.29. It's wrong. Like precision cannot be over 100%. It has to be between 0 and 1. That is between 0% and 100%. All right. So the only person that got it here, let's quickly look at it and see what the answer is. So for precision, precision is what? The total, let's look at it here again so we work together. Is the ratio of the true positive predictions to the um total predicted positives. The true positive predictions. All right. So we're going to come here. And how many predictions do we have here? Positive prediction. We have 175. All right. So the problem here now is that it didn't even get up to the actual it didn't get up to the number of actual positive predictions, but at least everything he predicted here were true. So the place that we have problem is in the negative predictions. All right. So we're going to come here and say at least it predicted everything that we have here were correctly predicted. So the true number, the correct, the number of true positive predictions are or is 175 divided by the total number of predicted positive, which is still what 175. So in this case, it is going to be 1 on or 100%. So that is our precision. Our recall will be, according to what we have here, is the ratio of true positive predictions. So what is the true positive predictions? Our true positive prediction is 175 divided by what? The total actual positive. So the total actual positive here is what? 200. So we have 200 here. So it's going to be what? 87.5%. So you can see how precision and recall works, right? So the person that got it is Abubakar Amidu, right? I think he's the only person that got it correctly, saying the precision is 100% and the recall is 87.5%. So yeah, as I said before, this can be a little bit tricky, but I needed to break it down for us in this way so as we understand exactly what is happening. How did we get 200? We got 200 from here, this positive, actual positive predictions. We got 200 from here, right? So let's just move on because of time. We still have some few things to look at. So we looked at precision and recall. Now F1 score. So F1 score is not really a different metric. So F1 score is just combining precision and recall, right? In the case where you actually don't want to focus on precision alone or you don't want to focus on recall, but you want to combine the two so that it gives you a balanced it just gives you a balance basically. You can use F1 score, right? F1 score is the harmonic mean of precision and recall, providing a single metric that balances both concerns. So depending on your task, depending on what you are doing, you can now decide on which particular metric to use. So the F1 score is useful when you need to balance precision and recall. That is for F1 score. So we look at let's quickly look at confusion matrix. So this confusion matrix is like a very very good metric. It kind of gives you an understanding, general understanding of the predictions. So the confusion matrix is a table that is used to describe the performance of a classification model in a set of test data for which the true values are known. So the four values that are concerned in the confusion matrix are what? True positives, true negatives, false positives, and what? False negatives. All right. So these are the four values that are computed in our confusion matrix. So you just need to know that the true positives are actually the number of correct positive predictions. So if you look at our positive predictions, we can get the true positives. Those ones that are actually correctly predicted as positives, they are the true positives. So the true negative are the ones that are correctly predicted as negative, right? They are both negative in the actual data set and also negative in the predicted value, right? That is for true positive and true negative. False positive are what? The false positives are predicted positives that are negative. That are the actual value is negative, but your model predicted it as positives. So that is what false positive is, right? False negative is the opposite. Your model predicted it as negative when the actual value is positive. So these are the different values that are used in confusion matrix. So what confusion matrix do is just to give you the value of the four of them. So it gives you the value of true positive, true negative, false negative, and what? False positive. So once you begin to see the implementation in Scikit-Learn, you are going to understand how to interpret confusion matrix, right? So you can see the formula of recall and precision. They are actually calculated from this true positive, true negative, and false negative, and all of that. So you can see recall is true positive over true true positive plus false negative. All right. So the same thing for precision here. So it's basically the same thing we did that time, but the difference is just the denominator, right? In this case, we are calculating in the precision, we are calculating focusing on just the positive predictions, while in the recall, we are focusing on the positive predictions and also the actual positive values. So these are the different formulas. You can see accuracy here, true positive plus true negative. So don't bug yourself or don't allow yourself to get confused over these different formulas here. So just understand what we did previously or just a few minutes back. So that is how you can understand these different metrics. So I think the reason why they even call it confusion matrix, I don't know why, but it might look confusing at first, but as you go on and implement it and use it in different models, you'll get very comfortable with it. So these are just illustrations. The material will be sent to us so we can look at it and gain better understanding. So that we've looked at very, very interesting metrics. We looked at accuracy, confusion matrix, precision, recall, F1 score. Now we'll look at ROC. Right, ROC is another metric used for classification algorithm. So the ROC is actually a curve, right? It is used to compare the performance of a model. It can either be used to compare the performance of a model at different threshold, all right, or it can be used to compare the performance of different models. Let's say you are using different algorithms to create different models. You can compare all of them using ROC curve and plot them in a graph like this. So the ROC curve is a graphical metric that shows you how well a model is performing. So the ideal curve should be something that is close to this point. So the curve should come up here and touch this place and go like so. That is the ideal curve. So the closer the curve is to this point, the better the model. All right, you can see the different model we have here. We have this blue. Between this, among all these lines we have your model, the best performing model is this blue curve because it's closest to this point here. Why this one is bad, this green one is not good. this. So you can see that this ROC curve is used to basically compare model. You might not necessarily grasp it fully now, but once we start implementing Scikit-Learn, you would understand it very, very, very well. All right, so that is it for that. AUC is alongside ROC, right? We are also going to look at that during Scikit-Learn. So just understand we have ROC and we have AUC. So they are used side by side. All right, so these are the different values and what they mean. Okay, so 1 is between 0 and 1 again. 1 mean is a perfect classifier, less than 0.5. So these are almost the same thing with what we've explained previously in the previous metrics. So we have this last one, which you'll probably not even use at all, right? Which is log loss, but I just wanted to include it. So these are the different metrics in classification algorithm. There are actually more than, and there are more of them than we have in regression task, and it's actually more tasking to evaluate a classification model than a regression model, right? More time and effort will be put into evaluating a classification model than a regression model. We are going to see what I mean by that when we start building our models. So we see the summary here. So this is a brief overview of all the metric that we've talked about so far, and when we can use it. So we have accuracy. Accuracy is used when classes are balanced and you want a general performance measure. All right. Precision is used when the cost of false positives is high. All right. Recall is used when the cost of false negatives is what? High. F1 score is when you need to balance precision and recall. ROC curve is to visualize the trade-off between true positive and false positive rates at various thresholds. AUC ROC to get a single measure of performance across all thresholds. And log loss when you need a measure that evaluates uncertainty of prediction. So these are the different metrics we have for classification task. So by understanding these metrics, you can better evaluate and tune your logistic regression models to meet the specific needs of your application. So yeah, that is it for that. You can see this diagram here. Classification metrics. We have logistic regression in the middle. We have accuracy. We have precision. We have recall. We have ROC. So these are the basic metrics that you'll be paying attention to when evaluating your classification model. So that is it. We've come to the end of the logistic regression class. We've actually looked at a lot. Let's just briefly go through it. We looked at what logistic regression is, the difference between logistic regression and linear regression. We looked at what logistic regression is, right? And we talked about the sigmoid function, which is the core functionality or the core differentiator between linear regression and logistic regression. It actually maps any input into probability values, right? So it converts any inputs you have to numbers between 0 and 1, which represent probability values. So we also talk about threshold, how threshold influence the class in which a particular prediction will fall under. All right. So we looked at the types of logistic regression: binomial or binary, multinomial, and ordinal. We talked about how ordinal and multinomial are different due to based on the labels or the categories being ordered or unordered. Then we moved on to look at the evaluation metrics. We looked at the accuracy. We looked at confusion matrix. We looked at precision. We looked at recall. We looked at F1 score, ROC curve, and AU. So all these things, as we are moving forward, we are going to be building on them. This is just a foundation, all right? So you will understand it better as we are building our models, right, and implementing it in code. So you need to understand these things. Like you need to get to understand all these concepts that we've talked about in linear regression and logistic regression. We're also going to talk about other algorithms, right? In the subsequent weeks, we are going to talk about decision trees algorithm. We're going to talk about KNN. We're going to talk about SVM. We're going to talk about ensemble learning. So, but these two, they are actually the introductory parts of machine learning algorithms. So moving forward, we are going to see other machine learning algorithms. But before we look at these ones, we are going to introduce Scikit-Learn and show us how we can start working with it. And your assignment too will also help you to practice as well. So yeah, we've come to the end of the class. It was actually a lengthy one. It's actually a lengthy one, and thank you for sticking up until this point. So now is the time for question. Please, if you have question, just raise your hand, and I'm going to be calling you up to ask a question. All right, Son the Alpha, please unmute yourself and ask your question. Son the Alpha. You're on mute now. Just unmute you so you can unmute yourself and ask your question.
Hello, good evening, sir.
Yeah, good evening.
Good evening, everyone. Thank you for the lecture so far, sir. I have a question to ask. And my question is, in order to choose the most suitable algorithm to deploy in developing one's model, isn't it advisable to perform an initial EDA, like exploratory data analysis, that will reveal the nature of your data, know if it made certain assumptions that will guide you in your choice of algorithm, rather than just going ahead, start checking your data to use a algorithm, only to find out that you have to make a lot of adjustment, that it has not made some certain assumption, and you have to start making adjustment here and there. Or if you find yourself in that kind of situation, what do you actually do, sir? I don't know if my question is clear.
Yeah, that's a good question. Definitely during your exploratory data analysis, some of the things you'll be doing are actually going to be evolving around understanding your data. So definitely after your EDA, you will know if your data it has any multicollinear, if there is any if your data is normally distributed, because you're going to check the numerical variables using histogram. So you do a lot of things basically, but there are some aspects of those assumptions that you can't actually check until you build your model. In cases of the residuals are only gotten after you build your model. So it's when you've built your model, you can now start checking the residual if they are independent. You start checking your residual if they are normally distributed. So most of these assumptions are actually based on the residuals or the error. All right. And there's no way you can check that before building your model. You have to build your model first before getting the error, and then using the error that you've gotten to check those assumptions. All right. But definitely you check your data, definitely before your building model. You check a lot of things during your EDA and all of that. So yeah, I think that's, I don't know if you are satisfied with the answer or if I was able to get your question. Are you okay with that, Mr. Sunday?
Okay with that. Thank you, sir.
What do you say?
I said thank you. I am okay with the explanation. But I was only
Okay.
thinking in the case of linear regression example, where we have an assumption, I can't remember precisely now, where the variable was, is it continuous or something? How do we check if the variable, maybe in your sample data now, how do you check, since you cannot, I don't know, what method do you use to check whether it has met that basic, that fundamental, requirement for linear regression before you can now decide that, okay, this I can use linear regression in this particular data set, like that.
Okay, the thing is, like I've said this thing already, that most of the data you'll be working with, all right, most of them meet these assumptions, right? But there's a core assumption which is linear relationship. So that is the one that you'd want to make sure that in case of linear regression now, let's just use it as an example. In case of linear regression, you need to make sure that your variables have a linear relationship, all right? And the only way to check that is by using visualizations to compare your independent variable against your dependent variable, right? To see how the relationship is, right? If there's any form of curvilinear relationship, or if the relationship is not linear, then you know that linear regression is not going to be the best, is not going to be the best suited algorithm for this task, all right? So that is the thing you would check most of the time if you want to decide on linear regression. But the other assumptions would have to be after you've trained your model, right? Once you've checked that particular assumption and it is met, you can now go ahead and train your model, and then the errors and the residuals cannot be used to confirm if the remaining assumptions are met. So don't allow this to give you much headache. Trust me, most of the data sets you'll be coming across, by the time you work with a lot of data sets, you would just know, like, okay, this is the although when you do your EDA, you see most of these things, but it's not a big issue. Trust me, it's not a big issue unless your model starts having very poor performance, right? It's not like you not check these assumptions, but the ones I just mentioned, which is linear relationship, is very, very necessary. But the other ones, as long as your model is performing well, which is the main thing, then you don't really have a need to go on to, unless you are required to. All right, so let's just move on to the next person, please. Ozioma, you can ask your question. Ozioma, unmute yourself and ask your question, please.
Hello, good evening, sir.
Yeah, good evening, sir. You can go on.
So I'm still trying to understand the recall. Question is, in what scenario should one prioritize prescription over recall? Hello? Network. Hello, sir.
Hello, can you hear me?
Yes, hello, sir. Can you hear me?
Yeah. I can hear you.
Okay. I said, in like the prescription and the recall, in what scenario should one prioritize prescription over recall?
Okay. It depends on the settings, right? So, for example, let's say what you are doing requires you, like, let's say the cost of false positives. What we mean by false positives, like, instead of the predictions, the model is predicting something to be positive when it is supposed to be negative. That is what false positive is. So let's say the thing you are doing, that prediction is actually very costly, and you want to minimize it. You want to make sure that you don't have plenty false positives. You use precision. Do you understand? For instance, now, for instance, you are maybe I give this scenario in medical diagnosis, maybe let's say in cancer screening. It is very crucial that the positive results, the positive predictions are accurate. Like, a false positive could actually lead to a lot of things, unnecessary stress, um, going ahead to perform surgery that are unnecessary and giving them treatments that they're not supposed to be getting and all of that. So, let's say you have a model and you apply that model to making predictions on cancer patients, and that person also, you want to know if someone has cancer. Basically, you don't know if that person has cancer or not. Let's say, for instance, I don't know, any kind of cancer, and that person actually does not have cancer. Like, that is the ground truth. But your model now predicted that that person has cancer. That is the case of false positive. And precision actually works to minimize that false positive. So if you have a high precision, like 95%, that kind of situation will not happen. Like, you will not have your model predicting positives when it is not supposed to, predicting positives when it is actually negative. All right. So this is an example. Like, in medical diagnosis, it can also be in other situations, like in financial sector, fraud detection, and all of that. So you just have to know that whenever you want to minimize false positives, you make sure that you prioritize your precision. You make sure that your precision score is high as possible. Understand? So domain is very, very important, like very, very important. We can't look at all domains in this case. So business understanding too will come in place to ensuring that you focus on the right metric. There are some cases where you need to focus on recall. There are some cases where you just need to balance the two. If your data set is balanced, you just use accuracy, all right? And it will just give you a general idea of the performance of the data. So there are a lot of things to talk about when it comes to classification metrics, right? There are a lot, but this is just a foundation just to give you an understanding to how we can evaluate classification models, all right? So yeah, I think I've been able to give an instance of that, and that should serve, all right? So if you have any
thank
further
you.
question as well,
No,
um,
thank you, sir.
put it out on the group chat. All right. So any other questions? So we'll call it a day. Any other question? All right. Shamsuddin, please go ahead. I think you'll be the last person.
Hello, good evening, sir.
Yeah, good evening.
My question is still on this evaluation matrix. So, for example, maybe probably I'm working on a health care data, but the data is not balanced. That is imbalanced data, but the imbalanceness of the data is not significant. Maybe probably the people having glaucoma are like 60, while people without glaucoma are like 50, which is the difference is only 10. So in this scenario, if I try to evaluate my model, which of the metrics will be more accurate for me to focus on?
Based on what we heard so far, you said the positive class is 60 and the negative class is 50. It's
Yes.
a fairly balanced data.
That
Doesn't
is
have to be.
okay.
Yeah, go on.
And same time the data is not normal distributed. It's not normally distributed. Assuming I'm using a figure for visual field, which visual field have number ranges from 1 to 45. So some of these points may have a value lower than threshold. So in that case, definitely we have the data is not normally distributed and the imbalance is not significant. And at the same time, I try to evaluate this model. So which of the metrics should I focus on, or the accuracy is still okay in that sense?
Yeah. This proportion that I just gave now is okay to use accuracy. So accuracy is a very good metric when your data is balanced. So your data, it doesn't necessarily have to be the same proportion. It doesn't have to be 50-50 or 60-60. As long as the difference between the two classes is not much, then it's balanced. It's actually fairly balanced. That is a realistic data set. So it's okay to go for accuracy as a metric. But if you need to focus on preventing false negatives or false positives, then you can now use precision and recall. But if you just want to get the general, you want to put everything into consideration, and accuracy is a good one, right? So there are a lot of factors actually to consider as well, right? A lot of background context to also understand before choosing or selecting a particular metric. So today's class is not going deep into all of that. It just give you a foundational knowledge on all of this evaluation metric. All right. So because of time, we'll just be closing the curtain here, so we can all go back to what we have to do. So tomorrow we'll continue with Scikit-Learn, right? And then look at the library, introduce the library. So we are not going to do much tomorrow. It's just to introduce the library and show you around what you can use Scikit-Learn for, and just a little bit of coding, right? So, and we proceed from there. And think in the next 2 weeks you should be getting your project. Next 2 to 3 weeks, either second week of September, you should be getting your project. So we're actually rounding up. So make sure that you are catching up, or you've caught up with everything we've been doing so far. So yeah, thank you very much for your time and your attention. See you tomorrow. Have a nice day. Please don't forget to do the needful. Post what you've learned in today's class in the group chat. Thank you very much and good night.